The universe has been stable for a very long time. Nothing has suddenly changed the way matter works, or the way forces hold things together. We just assume it will continue. When we think about the universe, we usually think about objects in it. Stars, planets, galaxies, the space between them. We don't often think about the space itself as something that has properties, or that could be in a particular state. The vacuum, the emptiness, just seems to be there, neutral and constant, allowing everything else to happen. It's treated as a background, something stable and passive, not something that could shift or change or settle into a different configuration. But that emptiness, the vacuum, isn't actually nothing in the way we usually imagine nothing to be. It has a state, a particular energy level. The way particles behave, the way forces operate, the fact that atoms can form and chemistry can happen, all of this depends on the vacuum being in the state it's currently in. We've been relying on that state for the entire history of the universe, without ever needing to check whether it's still holding, whether it might be temporary, whether it's really the most stable arrangement possible. There's an idea in modern physics that the vacuum we exist in might be what's called a false vacuum. The term sounds technical, almost abstract, but the concept is strangely physical. If the vacuum is false, it means the state it's in right now, the configuration that allows our kind of matter and structure to exist, might be stable enough to last for billions of years, maybe longer, but it's still sitting at a higher energy level than it could be. Like a ball, resting in a shallow depression on the side of a hill, with a much deeper valley somewhere below. The ball isn't rolling. It looks settled. But it's perched in a place that isn't the lowest point it could reach. The physics suggests that if the vacuum somewhere were to shift into that lower state, well, the change wouldn't stay localized. If it transitioned from false to true, the change wouldn't stay localized. The new vacuum would expand outward in a perfect sphere, moving at the speed of light, replacing the old vacuum as it spread. And inside that sphere, everything would suddenly be subject to different rules. The particles we're made of might not be able to form in the same way. The forces that hold atoms together might operate differently, or cease to work at all. Whatever structures had been there, stars, planets, molecules, life, would find themselves in a space where the foundation beneath them had changed, where the vacuum no longer supports the kind of existence they require. This isn't the same as the edge of the observable universe, where we simply can't see farther, because light hasn't had enough time to reach us. This is something else. A boundary that could form spontaneously, anywhere in the universe at any moment, separating a region where our physics works from a region where it doesn't. A moving edge beyond which the vacuum has shifted into a state that doesn't allow the kinds of processes and structures we depend on. A point in space where existence, in the form we recognize, would simply stop being possible. The unsettling part is that there would be no warning. The bubble of new vacuum expands at the speed of light, which means the light that might tell us it's coming would arrive at exactly the same moment as the transition itself. One moment, the vacuum would be stable, the same as it's been for billions of years. The next moment, for anything in the path of that expansion, the rules would have changed completely, and the kind of reality we live in would no longer be compatible with that space. There's a quiet strangeness to the thought that somewhere in the universe a point could exist where reality itself has shifted into a different mode, where space is still there, where the geometry of the universe continues, but where the baseline state, the vacuum, has dropped into a configuration that doesn't support matter as we know it, forces as we understand them, structures that can persist over time, a boundary moving outward, beyond which our kind of existence cannot continue, simply because the foundation has changed. We assume the vacuum is stable, because it's been stable for as long as we've existed, for as long as stars have been forming, for as long as atoms have been able to hold together. But if this idea is correct, that stability might be conditional. The vacuum might be sitting in a state that works, that allows the universe to function the way it does, But it might be sitting there only because nothing has disturbed it yet. And if it were disturbed, if it shifted into a lower state, a new kind of boundary would begin to exist. A point beyond which the universe is no longer arranged in a way that permits the kinds of interactions, the kinds of structures, the kinds of processes that everything we know depends on. Stability might only look stable from our position in time, or maybe just from how short our position in time actually is. We experience the universe as something that's been consistent for billions of years. The same forces, the same particles, the same rules. And from that perspective, it feels permanent. But billions of years is still just a duration, a very long one from our view, but not necessarily the kind of timescale where we could tell the difference between something truly stable and something that's just been holding for now. If the vacuum we're in is false, if it's sitting at a higher energy level than it could be, there's no particular reason it would have to transition. No schedule. The system could stay that way indefinitely, or it could shift tomorrow, or in a trillion years. The physics doesn't give us a timeline. Not a useful one anyway. It just says the possibility exists. That somewhere, at some point, the vacuum could tunnel into a lower state the way quantum systems sometimes do, jumping from one configuration to another without passing through the middle. And once that happens, once the new vacuum appears somewhere, the rest is almost mechanical. The lower state is more stable, so it expands outward, replacing the higher state as it moves. A little like a phase transition, the way ice spreads through water when the temperature drops below freezing. Except it's not temperature that's changing. It's the baseline state of space itself. And the transition moves at the speed of light, which is the fastest anything can propagate through the universe, the fastest any change can spread from one place to another. The boundary itself would be... It's hard to say what it would actually be like. We can't observe it directly. We can't stand outside and watch. If the transition were happening, we'd either be outside the bubble, where everything still works the way it always has, or we'd be inside, where the rules have already changed. There's no gradual shift between them, just a division, moving outward, separating one kind of vacuum from another. From far away, if you somehow had time to watch before it reached you, you might see something odd happening to the light coming from the region where the transition had occurred. Light behaves according to the properties of the vacuum it's traveling through, so if the vacuum inside the bubble is different, the light might change, or disappear, or shift into something we wouldn't recognize as light anymore. But you wouldn't see the boundary approaching, you'd just see the effects. A region of space where the signals stop making sense, where the photons arriving from that direction have properties that don't match what we expect. There's something limiting about being inside the system we're trying to understand. Every measurement we make, every observation, every piece of data we collect, all of it happens within the same vacuum state we're investigating. We can't step outside to get a different perspective. We can't compare our vacuum to another one and see how they differ. All we can do is build models, run calculations, try to infer what other states might be possible based on the equations we've developed. And those equations themselves are built on observations made entirely within this vacuum. We're trying to understand the container from the inside, with no view of what might exist beyond it or what the container itself is resting on. And then, the boundary would reach you. The new vacuum would arrive at your location, moving at light speed, and the old vacuum would be replaced. Whatever physics had been operating there, the forces holding atoms together, the way particles interact, the way energy moves through fields, all of that would shift to match the new state. Whether atoms could still form after that, whether stars could still exist, whether any kind of structure could persist, that depends entirely on what the true vacuum is like. And the equations don't really tell us that. They just say it's lower in energy, more stable. They don't specify what happens to everything else when the transition occurs. They just stop short of that. It's possible the true vacuum is close enough to ours that some version of structure could still exist. Different particles maybe, different forces, but still organized in ways that allow complexity to build. Or it's possible the true vacuum is so different that nothing like matter could form there at all. That the fields settle into a state where particles just don't appear, where forces don't operate in the same way, where space itself might still be there, still continuous, still geometric, but empty in a way that's more fundamental than what we usually mean by empty. We treat the vacuum as if it's neutral, passive, just the background that allows everything else to happen. We don't think about it having properties, or being in a particular configuration, or needing to remain stable for matter to exist. It's just there, and it's been there for so long, supporting the same kinds of processes, allowing the same kinds of interactions, that we've never had to question whether it might shift, whether it might be temporary, whether the foundation everything rests on is really as solid as it seems. Every time we run an experiment, every time we measure a force or observe a particle or test a theory, we're implicitly assuming the vacuum hasn't changed. That it's the same today as it was yesterday, the same now as it was when the universe was young. We don't check. We just assume. We don't have a way to test whether we're in a false vacuum or a true one. We can't make a true vacuum in a lab and observe what happens. We can't point a telescope at a region where the transition has already occurred and see what it looks like. All we have are the theoretical models, the mathematics that describes how fields can exist in different energy states, how vacuums can be stable or metastable, how transitions might happen, and those models allow for the possibility that we're in a false vacuum. They don't say it's certain. They don't say it's likely. They just say it's allowed by the physics. If that's true, then we're already living inside something that only looks permanent because it's lasted this long. The vacuum holds because it's been holding. The forces work because they've been working. The particles exist because they've existed for the entire span of time we can observe. And all of that has been enough. Enough to build galaxies, stars, planets, life, everything we know. But that history, as long as it is, doesn't guarantee anything about tomorrow. It doesn't tell us whether the state we're in is truly the lowest it can be, or whether it's just low enough to have stayed this way so far. It just tells us what's worked so far. There's something about distance we think we understand. A galaxy too far away to visit. A region of space we'll never reach because it's receding faster than we could travel. Those are limits we can picture. They're frustrating maybe, but they make sense. The place is still there. The physics still works the same way. If you could somehow cross that distance, if you had enough time or speed or technology, you'd arrive somewhere that operates under the same rules. Atoms would still hold together the way atoms do. Light would still behave the way light behaves. You'd still be made of the same kinds of particles, held together by the same forces. A region where the vacuum has transitioned into a lower state, that's not the same kind of limit at all. It's not about distance. It's about compatibility. The space is still there. The geometry continues. But the foundation beneath everything, the vacuum state that determines what kinds of particles can exist, what forces can operate, what interactions are possible, and that foundation is changed. And if the foundation changes, then the kinds of structures that were possible before might not be possible anymore. You couldn't just visit that region and observe it, because the you making the journey depends on the vacuum being in the state it's currently in. Change the vacuum and the matter you're made of. The forces holding your atoms together. All of that might stop working in the way it needs to for you to continue existing. It's strange. We don't usually think of existence as something that depends on a background condition like that. We treat it as more fundamental. Either something exists or it doesn't. But this suggests there's something beneath, a substrate that has to be in the right state for existence, in the form we recognize, to even be possible. The vacuum provides that substrate. It's what allows particles to have mass, forces to have strength, fields to interact. And if the vacuum shifts, the substrate changes. What was stable before might not be stable anymore. We assume the vacuum is uniform because everywhere we've looked, it appears to be the same. Every measurement we've made, every observation, Every experiment, all of it has been consistent with the vacuum having identical properties throughout all of space. So we extrapolate from that. We assume what's true here is true everywhere. What's true now will remain true. And that assumption has held for the entire history of the universe we can observe. But it's still an extrapolation. The models allow for the possibility that the vacuum could be different in different regions, that a transition could create a boundary between one vacuum state and another, a division between areas where different rules apply. If that happened, if a bubble of true vacuum formed somewhere and began expanding, the boundary wouldn't be something you could see approaching. It moves at the speed of light, which means the light carrying information about the transition arrives at exactly the same moment as the transition itself. From any fixed point in space, everything would appear normal right up until the instant the boundary reached that location. No warning, no gradual change. At least, none we could ever notice. Just the old vacuum one moment and the new vacuum the next, and whatever consequences follow from that shift. Whether particles can still form, whether atoms can hold together, whether any kind of structure can persist, those consequences would begin immediately. There's no gap between the information and the event. That's what makes it different from other kinds of boundaries we're familiar with. Usually you can see something coming before it arrives. Light from a distant explosion reaches you before the shockwave. A signal travels ahead of the thing it's signaling. But when the transition itself moves at light speed, and the light that would tell you about it also moves at light speed, they arrive together. The first moment you could possibly know about the change is the same moment the change reaches you. It makes me think about what we depend on without realizing it. The vacuum isn't just empty space. It's not neutral or passive in the way we usually imagine emptiness to be. It has properties. It has an energy state. And all the physics we observe, all the particles, forces, interactions, they work the way they do because the vacuum is in a particular configuration. We don't check whether that configuration is still stable. We don't verify that the vacuum hasn't shifted since the last time we measured something. We just assume continuity. We assume the foundation is still there, still supporting the same kinds of processes it's always supported. A fish lives in water. It doesn't just occupy water. It depends on water having certain properties. Density, temperature, the way molecules interact with each other and with the fish's body. If water suddenly became something else, not colder or warmer, but fundamentally different in its structure, the fish wouldn't just be in a new environment. It would be in a place where the processes keeping it alive couldn't function anymore. The vacuum is similar in that way. Or, at least that's the closest comparison we have. We're built on top of it. Our atoms, our chemistry, the way energy moves through our bodies. All of that runs on the assumption that the vacuum has specific properties and will continue to have those properties. Change the vacuum, and the foundation shifts out from under everything that depends on it. We can't test this. We can't create a true vacuum in a controlled setting and observe what happens. We can't point instruments at a region where the transition has already occurred and study the effects. All we can do is run the mathematics, follow the equations, see what they allow. And they allow for the possibility that the vacuum we're in is metastable, that it could transition to a lower state. They don't say it's happening. They don't say it's likely. They just say, it's permitted by the physics. If the universe did contain a region where the vacuum had transitioned, where the true vacuum had replaced the false one, we'd have no way to know until we encountered it. No observation from a distance, no gradual change in the properties of light coming from that direction. The region might look normal from outside, or it might not emit light we'd recognize at all, or the signals might just stop making sense at some point. But we wouldn't see the boundary itself. We wouldn't watch it approach. We'd just see the effects, or we wouldn't see anything. And then at some moment the boundary would arrive and the vacuum state at our location would change. That division between regions, between a place where our vacuum holds and a place where it's transitioned into something else. It's not a wall or an edge in the usual sense. Space continues across it. The geometry doesn't break. But the baseline state, the configuration that determines what's possible, that changes. And because it changes, the two regions become incompatible in a fundamental way. Matter that exists on one side might not be able to exist on the other. Forces that operate in one region might not operate in the other. The kinds of structures we recognize. Stars, planets, molecules, anything complex. Those might require the vacuum to be in our current state. Change the state, and they might not be able to form at all. We talk about the universe as if it's one continuous thing, governed by one set of laws, with the same constants applying everywhere. And as far as we can tell, that's true. But if a vacuum transition occurred, that uniformity would end. You'd have regions with different physics, different rules, different kinds of existence permitted or forbidden, depending on which vacuum state was in effect. And between those regions, a boundary that doesn't stop expanding until, well, the models don't give an endpoint. The lower energy state is more stable, so it keeps spreading, replacing the higher energy state wherever it goes. The strange part is that this boundary, if it exists, if it's forming somewhere, we have no way to know about it until it reaches us. And by then it's too late to observe it from outside, too late to study it, too late to understand what happens at the transition. We'd just be inside the new vacuum, subject to whatever rules apply there. Or we wouldn't be at all. Every observation we make, every measurement, every experiment, they all depend on the vacuum being stable during the time it takes to make them. We don't usually think about that. We set up an instrument, we take a reading, we record a result, and we assume the underlying structure of space hasn't changed between the start and the end of the measurement. That assumption is so fundamental we don't even notice we're making it. It's just there. But if the vacuum is metastable, if it could transition at any moment, then every successful measurement is also a kind of confirmation that the transition hasn't happened yet. At least, not here. Not during the seconds or minutes or hours we were looking. It's a strange kind of verification. We're not actively checking whether the vacuum is stable. We're just noticing that physics still works, that particles still behave the way we expect, that the constants we measured yesterday are still the same today. And from that, we infer continuity. We assume the vacuum hasn't shifted because if it had, things would be different. Measurably different. Immediately different. So the fact that everything still works becomes a kind of passive evidence that the foundation is still there. But that evidence only covers the moments we were observing. It doesn't tell us anything about the moments in between, or the moments after, or what's happening in regions of space we're not looking at. The vacuum could be transitioning somewhere right now, a bubble forming billions of light years away, expanding at light speed, heading in our direction. And we'd have no way to know. The light that would carry that information is traveling at the same speed as the boundary itself. They're moving together, so the warning and the event would arrive simultaneously, and there'd be no gap, no advance notice, nothing we could detect or prepare for. There's something about that, the way the information and the change are locked together, that makes it feel more absolute than other kinds of limits. Or at least, harder to escape. Usually, limits have some give to them. You can see a storm coming before it hits. You can feel an earthquake starting before the main shock arrives. Even light from a distant supernova reaches us long before any material from the explosion could. There's always some separation between the signal and the thing being signaled. When both move at the same speed, though, when the fastest possible signal matches the speed of the transition itself, that separation collapses. There's no advance information, just arrival. We're used to having time to respond, to adjust, to prepare for changes we can see developing. This kind of boundary wouldn't allow that. It would just arrive. And in the moment it arrived, the rules would change. The vacuum state would flip from one configuration to another, and everything that depends on the vacuum being in a particular state. Everything from fundamental particles to complex structures to whatever processes are happening at that location would suddenly have to operate under different conditions, or wouldn't be able to operate. I keep coming back to the idea of compatibility. It's a word we don't usually apply to physics. I don't know if that's the right word, but it's the closest one. We think of physics as universal, the same everywhere, applying to everything equally, but compatibility suggests conditions that have to be met, requirements that need to be satisfied for certain things to exist, for certain processes to occur. And if those requirements change, if the baseline state shifts into a different configuration, then what was compatible before might not be compatible anymore. A particle exists because the vacuum allows it to exist. The vacuum provides the field configurations that give the particle mass, that determine how it interacts with other particles, that define what forces it responds to. Change the vacuum, and those configurations change. The particle might not be able to form in the same way. It might have different properties, or it might not exist at all in the new vacuum state. And if particles can't exist, then atoms can't form. And if atoms can't form, then everything built from atoms, molecules, chemistry, structure, complexity, all of that becomes impossible. The foundation required for those things to exist has shifted into a state that doesn't support them. It's hard to picture what that would look like from inside. We can describe it mathematically. We can run the equations. We can calculate how the fields would behave in a different vacuum state. But imagining the experience of being in a place where the vacuum has transitioned, the being part might not be possible. Consciousness, thought, experience, those all depend on physical processes running in brains made of atoms held together by forces that require the current vacuum state. Change that state, and the processes stop. Or they change so fundamentally that, well, they wouldn't be the same processes anymore. We assume we'd notice if something that fundamental changed, that there would be some signal, some indication that the foundation beneath physics was shifting. The models suggest otherwise, though. They suggest the transition would be sharp, instantaneous from any local perspective. One moment, the old vacuum. The next moment, the new vacuum. No in-between state. No gradual transition where you could feel things starting to change. Just a boundary moving through space at light speed, and when it reaches you, the switch happens immediately. There's a fragility to that. We think of the universe as robust, as something that's been stable for billions of years and will continue to be stable for billions more. And maybe that's true. Maybe the vacuum we're in is the true vacuum, the lowest possible energy state, and there's no transition waiting to happen. Or maybe we're in a false vacuum that's stable enough to last for timescales far longer than the current age of the universe. The models don't tell us which one we're in. They just say both are possible. And if we're in a false vacuum, a transition could occur. Every moment that passes where the vacuum hasn't transitioned, that's another moment of stability we can add to the history. Another day, another year, another million years where the foundation held. And from that accumulated history, we build confidence. We say the vacuum is stable because it's been stable for so long. But that's inference from duration, not knowledge of the underlying state. It's just saying. So far, it's worked. So far, nothing has triggered a shift. So far, we've been existing in a vacuum state that permits our kind of existence. We measure things constantly. Temperature, pressure, electromagnetic fields, gravitational effects. We're always checking whether the universe is behaving the way we expect it to. And every time it does, every time a measurement comes back consistent with previous measurements, we're implicitly confirming that the vacuum hasn't changed, that the baseline state is still the same. But we're only sampling tiny regions of space, brief moments of time. The universe is vast and most of it is completely unobserved. The vacuum could be transitioning in regions we've never looked at, will never look at. Can't look at because they're too far away or receding too fast. And we'd never know, unless the boundary eventually reached us. The boundary, if it exists somewhere. If a transition has already occurred in some distant region of the universe, it would be expanding outward, replacing the old vacuum with the new one, creating a growing sphere where different rules apply. And that sphere would be invisible to us until the moment it reached us. We couldn't observe it from a distance. We couldn't track its approach. We'd just be living in the old vacuum, assuming continuity, assuming stability, right up until the instant the boundary arrived and the vacuum state at our location changed. There's something unsettling about being inside a system you're trying to understand, with no way to step outside and see the whole structure. We can model it, we can calculate what might happen, we can describe the physics of a vacuum transition in abstract terms. But we can't verify those models against reality. We can't test whether the vacuum we're in is false or true. We can't measure how close we are to a transition, or whether one is even possible. All we can do is observe that the vacuum has been stable so far, and extrapolate from that. And if the boundary did arrive, if the vacuum state at our location suddenly shifted from false to true, there wouldn't be a story we could tell about it afterward. No record, no observation, the very structures that would allow recording or observing, the instruments, the data storage, the processes of measurement, all of those depend on the current vacuum state. Change the vacuum, and those structures might not function anymore. They might not exist in any recognizable form. The transition would be, it's hard to even say what it would be. An ending, maybe, or a transformation so fundamental that the categories we use to think about existence wouldn't apply anymore. The vacuum has been the same for the entire history we can observe, as far as we can tell. Every star that's ever formed, every galaxy that's ever taken shape, every chemical reaction that's ever occurred, all of it has happened within the same vacuum state. We have no experience with a different one, no comparison point at all. We can't say what it would be like if the vacuum were configured differently, because everything we know, everything we've measured, everything we've built our understanding on, it's all derived from observations made in this particular state. That makes it hard to think about alternatives. When we imagine a different vacuum, we're still using concepts that come from our current vacuum. Particles, forces, fields, energy. But those concepts might not translate. They might not even apply. The true vacuum might operate in ways that don't map onto the categories we use. It might have particles we wouldn't recognize as particles, forces that don't behave like forces, interactions that don't fit our models. Or it might be simpler. Fewer types of particles, fewer forces, less structure. We don't know. The equations tell us there could be a lower energy state, but they don't specify what that state looks like in detail. We're building our understanding of the universe from the inside, using tools and concepts that only make sense within the current vacuum state. It's like trying to understand architecture when you've only ever been inside one building, and you've never stepped outside. You can study the walls, the ceiling, the way rooms connect to each other, but you don't have a view of what's outside, what the building is resting on, whether there are other buildings nearby with completely different layouts. You're limited to what you can observe from your position. And our position is inside the vacuum, surrounded by it, made of particles that depend on it, using forces that require it to be in this state. Every thought we have, every measurement we take, every theory we build, it all assumes the vacuum continues to have the properties it currently has. We can't think outside that framework, because thinking itself requires physical processes that depend on the vacuum being stable. If a transition did occur, if the boundary reached our location and the vacuum shifted into a lower state, we wouldn't experience it as a process. There'd be no moment of transition where we could feel things changing, no warning phase. The shift would be instantaneous from any local perspective. One moment, everything operating under the old rules. The next moment, the new rules in effect. Or, no moment at all, if the new vacuum doesn't support the kinds of processes that create moments of experience. It's strange to think about time that way. We treat time as continuous, as something that flows regardless of what's happening in space. But time, as we experience it, as we measure it, that's also dependent on physical processes. Clocks tick because atoms oscillate. We perceive duration because neural processes unfold in sequence. If the vacuum changed in a way that prevented those processes from occurring, would time still exist in any meaningful sense? I'm not sure that question even has a clear answer. The geometry of space-time might continue, but the markers we use to track time, the experiences that give us a sense of its passage, those might not be possible anymore. We assume the universe is stable because we're still here, because we can still measure things, observe things, think about things. Every moment of continued existence is evidence of a sort, or at least we treat it that way. Evidence that the vacuum hasn't transitioned yet, that whatever state we're in, it's stable enough to have lasted until now. But it's passive evidence. We're not actively testing for stability. We're just noticing that we're still able to notice things. There's a difference between being stable and being permanently stable, though. A system can hold for a very long time and still be metastable, still be sitting in a configuration that could, under the right circumstances, shift into a lower state. The vacuum might be like that, stable enough to have supported the universe for 13 billion years, but still not in the lowest possible energy configuration, still perched in a state that could, theoretically, transition. The transition would create a boundary, a moving division between regions where the old vacuum holds and regions where the new vacuum has taken over. And that boundary would be sharp, not a gradual blend, not a transition zone where the vacuum is somewhere between the two states. Just one state on one side, a different state on the other, and a dividing line moving through space at the speed of light. We've never encountered a boundary like that. Every boundary we're familiar with, atmospheric layers, temperature gradients, the edge of a material, they all have some thickness to them, some region where the properties gradually shift from one side to the other. But the vacuum transition would be different. The quantum field either has one configuration or another. There's no intermediate state. So the boundary would be infinitesimally thin, I suppose. As strange as that is to imagine, a surface with no thickness, separating two fundamentally different vacuum states. If you were somehow able to watch that boundary from outside, if you could see it without being affected by it, you might not see anything at all. The boundary itself isn't made of matter or energy. It's just the edge of a region where the field configuration has changed. The only way to detect it would be through its effects, through what happens to matter and energy when they encounter it. And those effects would depend entirely on what the new vacuum state is like, what kinds of particles and forces it permits, whether anything from the old vacuum can persist in the new one. We talk about this as if it's a distant possibility, something that might happen somewhere far away, or in the distant future, or never. And maybe that's accurate. Maybe the vacuum we're in is truly stable, and there's no transition waiting to happen. Maybe the physics we observe is the only physics possible, and the idea of a false vacuum is just a mathematical curiosity, something the equations allow but reality doesn't actually use. Or maybe we're living in a false vacuum right now. Maybe the stability we've observed for billions of years is just luck, in a sense. The vacuum holding in a higher energy state because nothing has disturbed it yet, nothing has triggered the transition, and at some point, tomorrow or in a trillion years or never, that could change. A quantum fluctuation somewhere could seed a bubble of true vacuum. The bubble would expand, and everything in its path would find itself in a new vacuum state, subject to whatever rules that state imposes. There's no way to prepare for that. No precautions we could take. No shelter we could build that would protect us if the vacuum itself changed. Because everything we could build, every material we could use, every structure we could design, it all depends on the current vacuum state. Change the vacuum, and the materials stop behaving the way they did. The structures stop holding together. The forces that kept everything stable, those forces might not exist anymore in the new vacuum. We're depending on something we can't control and can't verify. The vacuum could be completely stable, locked into the lowest possible energy state, incapable of transitioning. Or it could be metastable, temporarily stable, sitting in a configuration that's been holding for billions of years, but could shift at any moment. And we have no way to tell which one is true. We just observe that it's been stable so far, and hope that continues. Every civilization that's ever existed, every thought that's ever been thought, every observation that's ever been made, all of it has occurred within the same vacuum state, assuming that state would continue. We've built entire sciences on the assumption of continuity, that the laws of physics are the same everywhere, the same at all times, that what we measure today will still be true tomorrow, that the foundation beneath everything will keep holding, and maybe it will. Maybe that assumption is justified, or maybe it's just the best we can do given that we're trapped inside the system, unable to see beyond the vacuum state we're currently in. There's something I keep circling back to. The idea that the transition would be instantaneous. That one moment you'd be in the old vacuum, and the next moment the new vacuum would be in effect. The mathematics says that the boundary moves at light speed, and when it reaches a location, the vacuum state flips. But I'm not entirely sure what that means physically. What happens to an atom in that instant? Does it just stop being an atom? Does it reconfigure into something else? Or does the concept of instant even apply when the fundamental rules are changing? We describe it as if there's a clean before and after, old vacuum, new vacuum. But the actual process, the moment when the field configuration shifts from one state to another, I don't know if we have a clear picture of what that looks like at the level of individual particles. The equations describe it in terms of field values changing, energy states transitioning. But fields are abstractions we use to organize what particles do, and if the particles themselves depend on the field being in a particular state, what happens during the transition? Is there a brief moment where nothing quite makes sense? Or does the shift happen so abruptly that there's no during at all? The models say matter from the old vacuum wouldn't survive in the new one, that the forces holding atoms together would change, or disappear, or operate differently. But wouldn't survive is vague. Does that mean atoms would disintegrate? Would the constituent particles still exist but just not bind together anymore? Or would the particles themselves? I'm not even sure how to finish that question. If particles are excitations of quantum fields, and the fields transition to a different configuration, maybe the old particles just cease to be meaningful as a concept in the new vacuum. Maybe there would be new particles, new excitations of the fields in their new state. But trying to imagine what happens to the old ones during that shift, it feels like asking what happens to a wave when the water suddenly isn't water anymore. We assume we'd know if the vacuum had changed, that there would be observable consequences, measurable differences, and maybe that's true. If the vacuum transitioned somewhere nearby, if the boundary was close enough to affect regions we can observe, we might see something odd. Signals stopping, light behaving strangely, stars in a particular direction just ceasing to emit in ways we recognize. But we're assuming we'd notice. That the effects would be obvious enough, clear enough, that they'd stand out against all the other complicated phenomena we observe in the universe. And I'm not sure that assumption is safe. Space is vast. Most of it is empty, or nearly empty. If a bubble of true vacuum formed in a region between galaxies, in a void where there's not much matter to interact with, would there be anything to signal the change? Would there be detectable effects? Or would the new vacuum just sit there, expanding silently, invisible until it encountered something dense enough to produce observable consequences? We might not see it until it reached a galaxy or a cluster, and by then, the boundary would already be crossing distances on cosmological scales, moving at light speed through regions we've never observed and never will. The timeline bothers me too. The models say the transition could happen at any moment, or never. That's not very helpful for understanding whether it's something to actually worry about or just a mathematical curiosity. Could happen at any moment sounds immediate, urgent. But quantum processes have strange timescales. A metastable state can persist for Well, for durations far longer than the current age of the universe, longer than we can meaningfully imagine. So saying it could happen doesn't tell us much about whether it will or when, or whether the probability is high enough to even think about. But then again, probability is a tricky concept here. The vacuum could transition via quantum tunneling, which isn't a process we can predict in the usual sense. It's not like decay, where we can measure a half-life and make statistical predictions. It's more like the system could spontaneously jump from one state to another, and we can't say when or how likely that is with any precision. So could happen at any moment might be literally true, and also completely unhelpful for understanding the actual risk. I wonder if the vacuum has already transitioned somewhere. If there's a bubble of true vacuum expanding in some distant region, billions of light years away, heading in a direction we'll never observe because the expansion of space is carrying it away from us faster than light can travel, or heading toward us, and we won't know until it arrives. The universe is so large. There could be processes happening at scales and distances we have no access to, changes occurring in regions we'll never see, boundaries forming and expanding in parts of space that are completely isolated from our observable patch. And we'd never know. We'd just continue observing the old vacuum, assuming it's the only vacuum until we encountered evidence otherwise. Or didn't. There's a limit to what we can infer from stability. The fact that the vacuum has been stable for 13 billion years tells us something. It tells us the vacuum hasn't transitioned here, in the region we can observe, during the time we've been able to observe it. But it doesn't tell us much about the future, or about distant regions, or about whether the current state is truly stable, or just stable enough to have lasted this long. We're sampling one location, one time frame, extrapolating from that to the entire universe, to all of time. It's a big leap. Maybe the vacuum is completely stable. Maybe there's no transition waiting to happen, no boundary that could form. Maybe we're in the lowest energy state already, and all this discussion is hypothetical, mathematical, not connected to any real physical possibility. That would be simpler, easier to accept. Or maybe we're in a false vacuum, and the stability we observe is temporary, contingent, dependent on nothing having disturbed the current state yet. And we won't know which until, we probably won't know at all. We'll either keep observing stability, or we won't. And if we don't, there won't be a chance to revise our understanding afterward. We go about our lives assuming the vacuum is stable, not consciously. It's not something we think about or check. We just assume the foundation is there, that the baseline state of space will continue to be what it's been, that the rules governing particles and forces will keep operating the same way tomorrow as they did yesterday. It's such a fundamental assumption that it doesn't feel like an assumption at all. It feels like just the way things are. Every measurement we make, every observation, every time we notice that physics is still working, we're confirming that the vacuum hasn't changed. At least not here. Not during the brief moments we were looking. The confirmation is passive, almost invisible. We're not testing for stability directly. We're just noticing that everything still behaves the way we expect it to. And from that, we infer continuity. The vacuum sits beneath everything. Particles exist because the vacuum allows them to exist. Forces operate because the vacuum provides the field configurations that make forces possible. Structure forms, chemistry happens, complexity builds. All of it resting on the assumption that the vacuum will maintain its current state. We don't verify that assumption, we can't really. We just proceed as if it's true, because proceeding any other way wouldn't make sense. If the vacuum is false, if it's sitting in a higher energy state than it needs to be, we wouldn't necessarily know. The state we're in has been stable for billions of years, long enough to build galaxies, form stars, allow planets to cool and life to develop. Long enough that stability feels permanent, I suppose. Like something that's always been true and always will be. But duration doesn't guarantee permanence. A system can hold for a very long time and still be metastable. still be perched in a configuration that could shift if the right conditions occurred. The boundary, if it exists. If a transition has happened somewhere and a bubble of true vacuum is expanding through space, we wouldn't see it approaching. The information travels at the same speed as the boundary itself. No advance warning, no signal arriving ahead of the change. Just the continuation of the old vacuum, looking stable, looking permanent, right up until the moment it isn't anymore. There's something about that. The way we depend on continuity, without being able to verify it, that makes the whole structure feel more fragile than we usually acknowledge. We treat the universe as robust, solid, governed by fixed laws. And maybe it is. Maybe the vacuum is in the lowest possible state, truly stable, incapable of transitioning. Maybe the foundation we're built on is as permanent as it seems. Or maybe we're existing in a temporary stability. A vacuum state that's been holding because nothing has disturbed it yet. Because no quantum fluctuation has seeded a bubble of lower energy. The physics allows for that possibility. It doesn't say it's happening, just that it could. That somewhere, at some point, the vacuum might transition. And if it does, a boundary would form. A division between regions where different rules apply. We can't know which is true from our position inside the system. We can observe that the vacuum has been stable so far. We can measure its properties, describe its behavior, build models of how it works. But we can't see beyond it. Can't compare it to alternatives. Can't test whether it's truly stable, or just stable enough to have lasted until now. Every experiment we run, every theory we develop, every observation we make, it all happens within the same vacuum state. We're inside the container, trying to understand the container with no way to step outside and see what else might be possible. The vacuum could be exactly as stable as it appears, or it could be metastable, holding in a configuration that's worked for billions of years but could still shift, and we're left inferring from what we can see, which is just the fact that it's been stable during the time we've been able to look. The models say a transition is possible. They don't say it's likely or imminent or something to worry about. Just possible. Permitted by the equations, allowed by the physics as we currently understand it. And understanding comes with uncertainty, with gaps, with questions we can't answer yet and might never be able to answer from our position inside the system. There's no observation we could make that would tell us the transition is coming. No measurement that would give us warning. If a boundary is forming somewhere, expanding through space at light speed, we'd have no way to detect it until it reached us. And by then, there'd be no time to observe, no time to measure, no time to understand what was happening. The change would just occur. The vacuum would shift from one state to another, and everything that depends on the current state would find itself subject to whatever rules the new state imposes. We assume tomorrow will be like today, because today has been like yesterday, and yesterday like the day before. The vacuum holds, the forces work, the particles exist. And from that pattern, we extrapolate forward. We build confidence that the stability we've observed will continue, that the foundation will keep holding because it's always held. But patterns aren't guarantees. Stability isn't permanence, and we're still depending on something we can't directly verify, just observing that it's been working so far. Every structure we know, every process we observe, every thought we have, it all assumes the vacuum continues, that the baseline state remains constant, that the foundation keeps supporting the same kinds of physics it's been supporting. And maybe that assumption is justified. Maybe the vacuum is stable in ways that prevent any transition from occurring. Maybe there are constraints we don't fully understand yet that make the current state truly permanent, not just temporarily stable. Or maybe the vacuum could transition. Maybe there's a lower energy state it could fall into. And the only reason it hasn't is that nothing has triggered the shift yet. No quantum fluctuation in the right place, at the right time, with the right energy to seed a bubble of true vacuum. And maybe that trigger will never occur, or maybe it already has somewhere far away, in a region we'll never observe. Or maybe it will happen here, tomorrow, or in a billion years. The models allow for all of those possibilities. They just don't tell us which one corresponds to reality. The vacuum has been stable for the entire history we can observe. Every moment we've existed, every star that's burned, every galaxy that's formed, all of it within the same vacuum state. That's a lot of accumulated time. A lot of evidence that the system is stable, at least on the timescales we can measure. But timescales they're relative. 13 billion years is a long time from our perspective. But compared to the kinds of durations a metastable system could persist, it might not tell us much about whether the vacuum is truly stable or just stable enough. We're left with the same uncertainty we started with. The vacuum could be false or it could be true. A boundary could exist somewhere, or it might not. The foundation we depend on could be permanent, or it could be temporary. And from our position inside the system, we can't tell which. We can only observe that it's been stable so far, that the physics we measure today matches the physics we measured before, that the vacuum appears to have the same properties it's always had. The universe keeps operating, space continues, galaxies form and drift apart, stars ignite and eventually fade. And beneath all of it, the vacuum, maintaining whatever state it's in, allowing the same kinds of processes to occur, supporting the same kinds of structures. Whether that will always be true, whether the stability we observe is permanent or provisional, we can't say from here. We just observe that it's been true until now.